All right, here we go. Unit 5, Lesson 4, the mean value theorem. So this is going to be another calculus theorem that we use, just like the intermediate value theorem, but we're going to learn about what's called the mean value theorem today. And so first I want us to start by considering the function to the right. It's the function negative 5x squared plus 4x on the interval 0 to 6. And recall that we have two definitions of this phrase, rate of change. From sort of algebra 1, algebra 2 land, we have the average rate of change. That's your normal just slope formula between 2 points. If we take the slope between point A, 0, 0, and the slope between point B, 6, 6, and we find the slope of that tangent line, right? Your standard y2 minus y1 over x2 minus x1, the average rate of change is 1. Second, we have the instantaneous rate of change. There's your calculus, right? The instantaneous rate of change, the rate of change at a single point. It's kind of like a hand clapping in the woods thing, right? Can you have change at a point? Calculus tells us yes, that's the derivative. It's the slope of the tangent line. And so, for example, the slope of the tangent line, the instantaneous rate of change at x equals 4 is 0, because if I drew a tangent line there, that one's kind of upward sloping, but you get the idea. The slope of that tangent line would be 0, because if you imagine it's like a ball going up and down, the ball has hit its peak height, it's neither going up nor down, it is stationary for one instant in time, the slope is 0. What the mean value theorem tells us is that if we have a function that is continuous, meaning I can draw this entire function without lifting my pencil, and it is smooth, meaning there are no sharp corners, there are no vertical asymptotes, there are no places where I can't take a derivative, then the mean value theorem tells us the following. This is a really important, this is a memorize it, this is a write it down. If a function is continuous and differentiable on some interval, then there is guaranteed to be at least one value of c on the interval a to b. So some value between 0 and 6 in the example above, where the derivative, the instantaneous rate of change, is equal to the average rate of change. Right? On the left, we have the derivative. On the right, we have the slope formula. If you have a continuous differentiable function, there will be at least one point where the instantaneous rate of change is equal to the average rate of change on that interval. Slope of the tangent line equal to the slope of the secant line. And this will play well on Desmos tomorrow, but what I'm basically saying is if you keep drawing parallel lines to your average rate of change, right? I'll try my best here. If you keep drawing parallel lines, if your function is continuous and differentiable, then what the mean value theorem tells us is there must be at least one, maybe more, but at least one point in time where the slope of the tangent line is exactly equal to that average rate of change. And based on my little drawing here, it looks like it's going to be at around x is equal to 3. And so we would say that at x equals 3, we have found a point that satisfies the mean value theorem, because we found the point where the instantaneous rate of change is equal to the average rate of change. Another way of saying this, right, it's commonly referred to as like the Autobahn theorem, the Autobahn, the road in Germany where you can go as fast as you want. If I know your average speed is 120 miles an hour, that means that at least one instant in time, you must have been going exactly 120 miles an hour. Maybe you went 120 the whole way. Maybe you went 100 and then you sped up to 140 to reach an average of 120, but there must have been at least one time where your speed was 120, where your instantaneous rate of change is equal to your average rate of change. That's the mean value theorem. We're going to do just a couple of examples of nuts and bolts here today because there's a couple of, like, especially for AP, like ticky-tacky things that you have to say in order to invoke to apply the mean value theorem. So let's look at this function here, 3 minus 5 over x. We've got it graphed below. It's h of x. Step by step. First, does the mean value theorem apply on the interval 1 to 5? So we're basically saying, does the mean value theorem guarantee that there will be a derivative equal to this average rate of change? And so if I were to estimate it here, the average rate of change looks like it would be up 1, 2, 3, 4 over 4. Looks like it would be equal to 4. But whether the mean value theorem applies is literally just asking us two questions. Is the function continuous? Yes, I can draw that function on 1 to 5 without lifting my pencil. Is it differentiable? Yes, it is smooth. There are no hard corners or gaps or jumps, so it is differentiable. So the answer here is yes. So therefore, yes. Graphically, what does the MVT guarantee for the function on the interval from 1 to 5? I've kind of already drawn that. It basically guarantees we are going to find a tangent slope exactly equal to that slope there. And if I were to kind of eyeball it here, maybe it's somewhere around there. Maybe it's a little bit above 2 would be my guess. It looks like this one's going to be a decimal, okay? So it guarantees at least one, maybe more, an instantaneous rate of change, slope of tangent, equal to the average rate of change, slope of secant. All right, so let's apply the MVT to find it. We already found the AROC of 4, the average rate of change. Just quickly, if I was like doing this as a free response question, I would say the average rate of change is, let's see, this is y2 minus y1, so 2 minus negative 2 over 5 minus 1. So we'd have here again, just 4 over 4. We have, oh, wow, okay, that was dumb. I had an A, that's why you do the math. The slope there is 1, not 4. So we have an average rate of change of 1. And so what the mean value theorem says, the mean value theorem guarantees at least one f prime of x, or to use, typically we say c, is equal to 1. And so f prime of x, if we just do a little bit of derivative here, h of x is equal to 3 minus 5x to the negative first. I like to do that first. So now we can say the derivative f prime of x is 5x to the negative second, using the power rule, is equal to 5 over x squared. And so what the mean value theorem tells us is that this derivative 1 will be equal to 5 over x squared, at least at one point. So we'd have here, if we just arrange this a little bit, we multiply both sides by x squared, we'd have x squared is equal to 5, x is equal to plus or minus the square root of 5, but we're only talking about the positive here, right? Because we're on the interval 1 to 5, so we're just talking about x is equal to the square root of 5. And so this value c, the square root of 5, as predicted, right, as predicted, is a little bit above 2. So that's that point right there, x equals the square root of 5, okay? And if you had a calculator, you could sort of plug that in and find what the y value is, but usually we just want the x value. So again, to summarize, the mean value theorem guaranteed there'd be another place, there'd be at least one place where the instantaneous rate of change is 1, and we found out that this happens at x equals the square root of 5 by applying calculus. All right, a couple more here. Explain why you cannot apply the mean value theorem on f of x equals x to the 2/3 minus 2 on the interval -1 to 1. So if you had this graph, right, easy. It's got a sharp corner, so it's not differentiable. this function f of x is not differentiable, therefore the mean value theorem does not apply. So if it was a graph, right, that's easy. If it wasn't a graph, right, the way you would show that you have this hard corner here is to say, okay, if f of x equals x to the 2/3 minus 2, well then f prime of x is equal to 2/3 x to the negative 1/3 minus 2, and here is where your problem is going to come from. Remember, x to the negative 1/3, this would be 2 over 3 times the cube root of x minus 2. 3 times the cube root of x minus 2. And so the problem here is that we know this derivative does not exist at x equals 0, right? Because you cannot divide by 0. It's a divide by 0 error. So if f prime doesn't exist at 0, then f is not differentiable at 0. Therefore, f of x not differentiable at 0, right? So you can get it with a graph. You can get it with a function. There are places where the mean value theorem does not apply. All right, doing well here. Just going to finish this off with one actual multiple choice question here from the AP exam and just one of the 4 parts of a free response question, so you can see what you would have to write on an FRQ to get credit. Let f be the function defined by f of x is x to the 3rd minus 3x squared. What are all the values of c that satisfy the conclusion of the mean value theorem of differential calculus on the interval? So, they've kind of even, if it's a polynomial, it's differentiable and continuous. We don't even have to worry about that. So literally what this one is saying is, first you need to find the average rate of change on 0 to 3. And again, I'm going to do all the work here, but it's a multiple choice. You would do whatever amount of work you needed to do. So we would have, this is going to be f of 3 minus f of 0 over 3 minus 0. So f of 3 would be, f of 0 is just going to be 0, so it's f of 3 that's tricky. This is going to be 27 minus 3 times 9. It's going to be 27 minus 27. We're going to have 0 over 3. Interesting. So we're going to have an average rate of change of 0. So this function, I don't know, this function probably looks something like this. It like goes up and then down, and we've actually found where the average rate of change is 0. So this, by the mean value theorem, there should be, some point in between where the average rate of change equals the instantaneous rate of change. So now we just need to find it. F prime of x, using the power rule, is 3x squared minus 6x. So I would set that equal to 0 because I want to know when the derivative is 0. So I want to know, when does 3x squared equal 6x? Divide both sides by 2x. So I want to know, this is just going to be when, so we'll do it one step at a time so it's guessing it. We'll have x squared is equal to 2x. Divided by x, we'll have x is equal to 2. And so what we're going to have here, this is going to happen just once at x is equal to 2. One more time, just recap. They told you to apply the mean value theorem. That's almost always going to require the same things. First, find the average rate of change on the interval you were given. Second, set the derivative equal to that average rate of change and solve for what value of x that occurs at. In this case, it happens at x equals 2. Okay, so now on to a final free response question, just one part of it here. What's really important here, this justification point is very difficult to earn. So I think we've actually done parts of this problem. We're given a table for some function g and its derivative. We're given a graph for some function h, and we're given this function f. You don't end up needing any of these. All you need is g, but I just want you to get, like, in the context of these problems, you do have to kind of pick out which function are they talking about. Is there a number c in the closed interval, -5 to 3, such that g prime of c equals -4? When they say this, is there a number, this is your clue. This is almost always going to be either the mean value theorem or the intermediate value theorem. And we'll do like a whole exercise where we go back and forth so you can see recognizing which is which. In this case, we're talking about the mean value theorem. Is there a number in the closed interval -5 to -3 such that g prime of c equals -4? One thing I'm realizing now I left out, but I don't want to go back and redo all this. There's a section up at the top where they say here, so I'm going to fill this in. They say like g of x is differentiable. They say like g of x is differentiable on -5 to 0. And so what I would say, what I would start this process out by saying is literally I would put a number 1 and I would say g of x is differentiable on -5 to -3, therefore continuous on -5 to -3. That's an important point. If you're differentiable, you're also continuous, right? You can't have a smooth function without it also being continuous. Therefore, the mean value theorem applies. Whenever you apply the mean value theorem, you have to state these conditions. Because if it's not, right, if I gave you a function like this, well, the mean value theorem wouldn't apply because I don't necessarily have to have a place where the slope is 0. Because if I have this hard corner here, the slope never will be 0. It goes straight from positive to negative. So it is important to say that your function is differentiable and continuous. Now that we know it applies, I need to see if there is a value of g prime of c equals 4. So I would compute the average rate of change of g of x on -5 to -3. Well, that's equal to g of -3 minus g of -5 over -3 minus -5. And you work this out. This is 2 on the bottom. G of -3 is 2. G of -5 is 10. So we'd have 2 minus 10. We'd have -8 over 2. We'd have this equals -4. And so I would finish this up here by saying, therefore, yes, g prime of c equals -4 at least one time. Great, and that is the mean value theorem.